No questions? Okay. I think that we stopped here last time and I was explaining finite automata. Did you guys hear me?
Yeah, we can hear you.
Okay. So finite automata, I explained that it's a machine which we use to represent to define the regular language, and we have some conditions for that. That is that finite automata must have one start state. This is revision. We already did this. If you see the first page of this, so definition, so the it has one start state minimum, at least exactly one start state, and may not have final state, maybe no final state, maybe one final state, maybe more than one final state, and the word should be finished at the final state. So then we can say that this is valid FA. Okay, so we did this last time, and I think that we finished this, and we need to start from here. So I also realized last time that if you have this kind of FA where which has no final state, still it is valid, but it does not represent any language. It represents just file language. So it's not necessary to have to represent the to define the file language. We should not have any final state. If we have a final state but there is no way to reach to that, so that also um, represent the same thing. So you can have, this is also the, I mean, machine which does not represent anything. It defines file language. uh, I explain how to draw from the transition table. Information is given, so how we draw the FA. So this is also we covered last time. I think here we stop, and I am starting from here. So here, if you see that I'm saying we need to draw. So let's think both way, huh? If I give you FA and I want to ask you draw the write the regular expression of that. So then how you write that? So then if you see this, so let's say this FA is given and I am asking you, can you please write the regular expression of this FA? So then it is like this. You need to see what is the condition that words will be accepted. So you need to start from the start state and need to reach to the final state. In this machine, if you notice that if you have one A here in the word and the word start from A actually and it reach to the final state, and then you do not care what you have. You may have only one A. This is the minimum thing which you require. And then after that, you don't need to worry about that. You may have A or B and as many times because it is on loop. So when we need to write the regular expression of that, we will see that, okay, it should start from A and then we don't care. So it means that A plus B whole star. So this is the regular expression of this. Okay? This is a way you think about how to write the regular expression. Don't worry about this part. This is the garbage collection. FA has this functionality that FA also take cares of the garbage collection. So FA will so now I'm giving you one more information which we did not discuss last time. Sometimes when we have a word, so it has three states. First state is word will be accepted, and the second state is word will be rejected. Okay. Now let's say I have a word and this word is BA. So now if I start from here, let's say not B, A, B, A, A. So I start from here, I have first input I reach here with A, and then B, and then A, and then A, and I stop here at the final state. I am, the word will be accepted. Okay. And now if I have a word which is BAA, I start from here, I go here, and then A, and then A, and I finish at non-final state, the word will be rejected. Okay. So now rejection has actually two categories. One category is fail, second category is crash. So in FA, it will always, when reject, it will always fall under the fail category. FA will never crash. What is crash? We do not FA, we will never see this thing in FA. So crash means, so first you understand fail. Fail means you have a word and you always find how to completely read this word in this FA, whether this word will be accepted or this word will be rejected. It will never happen that you are somewhere in the middle of the word and you do not find you do not find at any state that, oh, how I handle A here. No, so this is not the case. Always every state in FA will take care of all A and B output. So if you see from this state A and B, from this state A and B, from this state A and B. So that's the reason that you will never stuck whether word will be accepted or word will be rejected. You will never stuck in FA. Okay, so you have a word, you will completely traverse that word, and when you are at the last letter, if you are at the final state, it will be accepted. If you are at the non-final state, it will be rejected, but it will be fail. It will never crash. Crash means you have a word, let's say just for example, I put C here and then A. So now I I'm here and I read first input and I get B here. Then I read A, I'm here. And then I have C. I'm not handling C here. So you did not completely traverse the whole word. You are somewhere in between or at the last letter or at the first letter or somewhere in between the word, and the word does not finish completely, and you do not know and you are not handling and on that state where I should go. So in this case, the word does not complete, still something left, but machine has no idea how to handle this input. Okay, in this case machine will crash. It is also rejection, but this is not fail, this is crash. Okay, so FA will never crash. FA will always have two states, either accepted or rejected, but rejected under the fail category. It will never crash. Okay, so you always take care of garbage collection. So all accepted or non-accepted words, you always take care of that. It will never happen that you have a word and you will not able to reject crash that. We will see this is its information in more detail when we see those machines which allow to crash. So we will see, so you will get more practical example of crash in those machines. FA will never crash. Okay, this is good. Now because FA will never crash, so this there is another information here. The complete name of FA is DFA. D for deterministic. But in short, we always call this FA, but actual its full name is DFA, deterministic finite automata. So FA is deterministic. What does it mean? That it has only one way of doing a job. So you will, so now if you have a word A and B, so there is only one way this word will be handled here. You will never see from any state more the same letter output more than one time. You will never see B is here and another B here. So if you are at this state, you will be confused that whether I should go this way or this way. You will never see this thing in FA. FA always take care of determinism, that it will always have unique output from each state edges. Okay, so FA is deterministic. So any when so there are two states also. One is deterministic, second is non-deterministic. Okay, so FA is deterministic. FA is not non-deterministic. We will see those machines which are non-deterministic, where from one state you have uh, duplicate outputs, but FA will never have duplicate outputs. If you have an FA which is something like that, so one state it is giving A on this side, and then there is another state it is giving A on this side also, so this is wrong. This is not valid FA. FA always have unique output. It will never duplicate the same letter more than one time from the same state. Okay, FA, and this is called determinism. FA is deterministic. It is not non-deterministic. Okay. So now you have this information. So now if I give you regular expression and ask you draw the FA of that. So how we draw that? So we need to see that in this FA, in this regular expression, it says start with A and then we don't care what's going on. So we have a state and this is a final state. So if you see this, this because from this one you will get lambda also. So minimum it gives you guarantee all words start from A, and it may be just A, but it will never have lambda, but it may be A, or after that we don't care whether it is B, it is A, or how many times because of A plus B whole star. Okay, so this is basically the word. So we are saying to reach to the final state you just need A, that's it. And once you reach at the final state, we don't care what's going on, whether A, comma B or B. So this will handle all the valid words. But as we know, FA is deterministic. It will also take care of the garbage collection, and from every state you need to handle, because in this case we assume summation is equal to, if this it is not given, A comma B. So you need to handle the second letter also B. So now we are saying, okay, what happens if you have B as an input at this stage? So, okay, if you have B, it should not go to the final state. It should go to some other state, which is a non-final state. Okay, and what happened? You after B, you have something else like B A, B B, or as many A's, as many B's. Okay, you are talking about loop A comma B. So now it will handle this one, and now we will check that whether the FA which we created is valid or invalid. It has one start state, valid. All edges have one letter as a label, valid. Every final state we don't care, we have final state or not, because FA has maybe no final state, maybe one final state, maybe more than one final state. So we have one final state, it is more than enough. um, and also whether it is deterministic or not, means every state should have unique output. It should take care of garbage collection, means every state should have outgoing edge of A or B. So you have this state, outgoing edge of A and B is valid. From this state, outgoing edge of A and B valid. From this stage, outgoing edge, I mean it is outgoing, but actually it is self loop, so it is A and B. So we have three states and every state is handling A and B. So this is valid FA. Okay. So that's the idea behind that. So Any question, guys? If you have any question here, what is because I explain a lot of things: deterministic, non-deterministic, rejection, fail, crash, accept. So, Quinton, garbage collection means uh, any machine has uh, some kind of words which are valid words. But what happen if you pass a word which is not valid for that machine? Like this machine will never accept any word which will start from B and end with anything else. It is invalid for this because if you see the regular expression, it will always accept all words start from A. So now if I have word BA, it is invalid for this machine. So this is a garbage for this machine. So is your machine is handling those words? So if you pass, so now we want to see that if we have this machine and you pass all the valid words to this machine, it is very good. This part of the design will handle that. But what happens if you pass a word which is not valid for this machine? Whether this machine will crash, mean it will stuck your system, you need to restart, reboot, or it can handle that also and say, no, sorry, this is invalid. Yes, it is handling that garbage also on this side. It is exactly like that if you write a code in C or C++ and you do some mistake, some wrong code, it does not stuck the machine. It does not hold or held the freeze the C++. When you execute, when you compile the code, it will tell you, oh sorry, this code is not good, it is invalid, it has this syntax problem, go to this page, this line, and this column, this row, and fix this. So it will tell you the idea of the template. From the template it has some information that it will guide you in line information that this is invalid. So this is basically garbage collection. Okay. So that's good. So now we are saying that. So this is. So what I meant to say, Quinton, it's very good that you ask a question. This FA will take care of garbage collection. This is property of FA. All machines do not take care of garbage collection. Those machines who does not handle invalid words, when you give some input or some those words which are invalid, they are not handling that. And let's say you are missing this part of the circuit, this part, and if you give a word which starts with B and you are not handling that, so machine will have input but does not know where to go because states are not handling that. So in this case, this word will be rejected, but it's not the fail, it's crash. Machine crash. So this is called crash. Okay, so it is like that. Now you know that to define one language, it is not necessary that you will have one regular expression. You can have more than one regular expression for the same language. Yes, we saw this in the regular expression chapter. So remember, if you have x uh, x plus actually x is yeah x plus or x x star or x star x x star. So these are same things. They give you guarantee that you will have one x and then after that as many x. So the same language but multiple regular expressions. So exactly the same thing here. So you can have multiple regular expressions to define the same language. Okay. So now if this is a case, so then you can represent more than one FA to represent the same language. So now the language which we have here, this one, let me clean this. So this language, this machine, so the same thing, we can have this FA. So if you see this, if you have B, it is the same thing, and A, you will reach to the final state. Instead, you have a self loop. You are saying A, B, you go to the final state. You add more than one final state, and then to handle the garbage collection in the last state, we have this AB also. So this will help you to take, I mean, not garbage collection, but because what happened if A and then one A and then after that you have more A's, so you need a loop here. So A and B, so you handle that. So this way you can beef up your the size of the machine, and you can have more than three states or four states or five states, and you can create the FA which will represent the same language. Okay, so this shows that you can represent uh, for the same language multiple FAs. So FAs are not unique for one language. Okay, so this is this idea behind that. So now if you want to extend that, so remove this loop here and add this as A comma B, and add a new state and add a loop here, so comma B. So this is the same thing. There is no difference here. So this one and this one and this one, they are all same. So you can do this also. Okay. So this is the idea behind that. So FAs are not unique. Now I think that we are good with this, and let's go to the next slide. So from languages to FA, there is not necessarily, so what I just explained to you, it is written here. A unique FA that accepts a given language. Is there always at least one FA that accepts each possible language that defines the language associated? Okay, now every now FA represents finite automata, or DFA, deterministic finite automata, represent regular language. Regular expression represent regular language. So every regular expression must have its equivalent regular finite automata, FA. It is not possible that you have a regular expression and you are not able to find or draw the FA of that. It is not possible. Okay, so if this language is a regular language, it must have at least one regular expression and one FA of that. It may have more than one regular expressions and more than one FA of that, but minimum it must have one regular expression and one FA of that language. It is not possible that this is a regular language and you might have FA but not regular expression, or regular expression but not FA. No, it is not it is not the case. If it is a regular language, it must be able to represent itself with at least one regular expression and at least one finite automata FA. Okay, so now it says that uh, build an FA that accepts all words containing a triple letter. Okay, so we want to create an FA which will either so which will so we don't care what will be the word, but it should have three A's or three B's. Okay, so it must have three A's or three B's. Now let me add a new slide here so I can draw this there. Okay. Now it says that build an FA that accepts all words containing a triple letter, either A or B. So it means it has whatever the word, anywhere, either in start or in end or in between, it must have either three A's or three B. So this is what it says. So might be, for example, it has a word B A B, or A B B B A, or just three A's or just three B's, or A, something like this, or it can start from A, or start from B. So anywhere in your word, you must have either this thing or this thing. So we need to draw the FA of that. Okay, so that's the idea behind that. So now, what is the thinking process? First, fulfill this condition which is required, that your FA will have three A's or three B's. So now we are saying, okay, we have this start state, and 1A, second A, and third A, and reach to the final state. We have this B, and then B, and then B, and reach to the final state. So this is the minimum requirement for this FA. So we draw the minimum requirement. Okay, but now we will. But you know that this machine just accept three A's and three B's. So what happened uh, if you have A somewhere in between? So might be you have word A and then three B's. So we are saying, okay, if you have A here and then three B's, so if you are here, because this is a valid word, if you have A and three B's, so then it means you need to go here and B. And now if you see A, B, 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 so you can have that. And the same way you can go here as A. So B, A, A, A. This is good. It can accept that. Okay. Very nice. So now what happen if you are at this stage A, and then you get three B's. So then you need to come here B and B, B. And what happen if you are here and then you have A there? So it is not recommended that you cross the line. So always you be go outside, which is A. Okay. So what happen if you are here and reach at A, and then you have uh, then you have three B's. So or A's. So we can have here A comma B. Or if you are here and then you have A or B. Now, I think that we handle all A's and B's, three A's and three B's. And if we see that whether we take care of garbage collection or not, first of all, this is valid FA because it has one start state exactly. Final states we do not care, but it requires here to have two final states. We add that. Let's see every edge is one letter, not more than one letter. So this is also valid. We check that. Now we will see that every edge has A and B outgoing edge is there to handle the garbage collection determinism. So first state A and B, good. This state A and B. This state A, B. This state A and B. Very good. This state A and B, two outgoing edge. This is state B and A, and this is state A and B. Perfect. So this is valid FA. It pass all the checks of to be valid, and beside it solve what we are saying that it can accept any word, but this word must have either A or B in it. Okay, so we just created that FA. Anyone has any question in this? Are we good? You guys understanding what's going on?
Yeah, it makes sense to me.
Okay. Anyone has any issue here, guys? Because we are not face to face. I cannot see you. I cannot see your face expression. Most of the time, I am very good to understand and reading the faces. But here, I am just relying on your verbal assurance that you understand this thing or not. So please let me know if you have any minor confusion in this, because this is also very important chapter. After that, life will be, it is not easy, but it will be not that technical. So this chapter is very technical, where you need to think and use your brain and draw this creativity and do. After that, it is just like math thing, 2 plus 2, like that. But it will be critical but not that hard. But this is the, you can say that something new. So So please, if you have any question here, let me know. So all of you, if you are not have any question and your silence, I will consider that as yes. Okay. And don't forget that you have to attempt the quiz today. So we will have one quiz today. There is, we don't have everybody here. Okay. Anyways. Okay, so if you have this, you understand this thing. So it is written here, build a partial FA that accepts A, add a path that accepts B, add paths for words that contain A's and B's before or after the A, or B. Exactly, I follow the same thing and I draw this. Okay. Now, every language that can be accepted by FA can be defined by regular expression. So if you have a language and you have an FA of that, you must have a regular expression of that language also. And every language that can be defined by a regular expression can be accepted by some FA. So you see, same thing what I just explained to you. It is not possible, it is vice versa. However, there are languages that are neither definable by regular expressions, not accepted by an FA. We will see what are those languages that which we for those uh, which for which we are not able to write the regular expression or FA. But for sure, those are not regular languages. Okay. So this FA and regular expression represent regular languages. That's the idea behind that. So now we need to draw an FA which will, so first of all, does this FA accept the word A, B? So this is something close to what we did last time. So it says that this FA will accept this language. So it will have, instead of 3 A's, it will have 2 A's. Okay. So now how we, so this FA uh, will accept either, if you see this, either 2 A's or 2B, and we don't care what happened before that, what happened after that. So how we draw that? So you have a machine and just 1A and 1B. Oh, sorry, another A. Okay, and then this is, I'm drawing the same thing with another idea. So 1B and another B. Okay, and now you are saying that uh, what happened if you are here in this state and you got B? What happened if you are here, you got BAA? So A. And once you reach at the final, you have whatever you have, you don't care. Once you reach at the final, whatever you have, you don't care. A comma B. Okay. So now, if you see uh, one start state and A and B, this is state A and B, and this is state A and B. This is state A and B. This is valid FA, and it is this. It accepts this regular expression. So we don't care what happened here. So now if you start, you have as many as A's or B's. You can start with A, you can start with B, A, B. You have loop here, and then after that A. So you can have all these things, and at end also you have loop, so you don't care what's going on after that. So you have loop here, you have loop here, and you have loop here also. Okay, so these are the loops here. So we can draw this regular expression by this. So this is one way, or you can, instead of two machines, you combine that with one final state, and it is the same thing. You can do that way also. Okay, whichever way is easy for you, so you can do that. But make sure that it should be valid FA. All states should have unique outgoing edges. If you see here, there is no duplicate edge. If at this state if you get A or B, you know that only one way to go to A, only one way to go to B. You are not confused that there are two A's here. No. So you always have unique outgoing edge. Here A and B. Here A and B. Here A and B. Here A and B. So let's look at this one. So we take care of all deterministic approach, and this is very nice valid FA. Okay, and this is the regular expression of this FA. Now you are saying that I want to draw a machine where this machine will accept all words which have for sure third letter B, and then I don't care what's going on after that. But whatever the word, its third letter should be B. So like if I have a word A, B, C, B, A, so this is wrong. This machine will not accept that because third letter is A. So this third letter will always be B, whether B, or A, B. First two letters I don't care, A or B. Third letter always B. After that I don't care what's happened. So this is the machine for that. So now if I say that how we do this, okay, listen. So first start here, and so you know that you A comma B means two outgoing edges, okay, and then second letter you don't care, A comma B, and this is second letter. Third letter, if it is B, it is good. It reached to the final state. And after that you don't care what's going on, A comma B. But here if it is A, it should go to another state which is non-final, and after that A comma B. So we don't care what's going on. So now if you see this, in the third letter it is B, and after that this is good. If it is third letter is A, it should go to the another path, and this is non-final state, and uh, it will be rejected, fail. Okay, so that's the idea behind that. So uh, how we write the regular expression of this thing? We are saying first letter may be A or B, second letter may be A or B, third letter just B. After that, we don't care what's going on. So this is the regular expression of this. Okay, so this is now easy. I believe that it is not hard. So if you have a question, so you can ask me. Okay, no question. So let's go to the next slide. So here this machine says that you want to draw the machine which will only accept one word. That's it. And that is BAA. So we have a machine. We have a machine which will accept only one word, B A A. That's it. So this is a perfect machine. It will accept. Now we make this FA a valid FA. We take care of garbage collection. What happens if you are here and you get A? It goes to the garbage. And what happens if you are here and after that A you have something, A or B, it will stay in the garbage. You are here, you got A is handling here, B goes to garbage. B goes to garbage. After that, if you have something, A or B goes to garbage. It will exactly accept only word BAA, and that's it. Even if you have BAA and after that something, it will be rejected. Look at this one. If you have word BAA, so BAA, so it will be rejected. So, but if you have exact BAA, it will be accepted. So this is the word. Okay. So a collecting bucket state for all other words. So this is a state which should take care of the garbage collection. So guys, any question in this if you are understanding or not? So hopefully you are there and you are happy with this. So let's see to the next slide. So here you are saying this is a machine which will accept two words only. One is VAA, second is AB, and then you are handling the garbage collection here the same way you were handling before. Okay, so this is a regular expression of this machine. It will accept BAA or AB. That's it. So big machine, small language. So it is taking more resources, but it is just accepting two words. Okay. So now we have another machine. So now my question with you is, uh, let's see who is here. Let's start from the Austin. So Austin Park. Do you think that this machine, uh, this machine is valid FA or not?
I don't believe it's valid because the final and start state are in the same block.
Okay, so this is not a problem. If you have a, so I mean, it can be, it is possible. It is not a problem. So it has one, it has, so now what are the, when we say that it is not valid, so we need to run all the possible checks of the machine. So does it has, first check, does it has strictly only one start state?
Yeah.
Very good. Final state, we do not care that we have one final state, we have no final state, or we have more than one final state. Final state can be anywhere, but we don't care about the final states for the validity. Does all the edges have uh, one letter per edge, A or B?
Yes.
Does all let states are taking care of unique outgoing edges and all outgoing edges for each A and B? So if you see here A and B, here A and B, yes. So this is a valid FA, okay? But yes, you are right. It has start state and final state at the same state. What does it mean? That this machine also accept lambda. So you are at the start state, from you always start traversing from the start state, and you did not give any input, and you are at the final state also. So what does it mean? It means that from where you start, right away, you whatever the word will be accepted. So and what is that word without any input, which is this is lambda. So it means that lambda is a word which does not have any letter. So it means that this machine will accept lambda. This is one thing. And then actually it is not doing anything after that. If you have A or B, it goes to here and A or B, and it will be not accepted. So this machine will accept one word, which is lambda, and this is a valid FA. Okay, so this is valid FA. So
Makes
now,
sense.
so Austin, are you clear now about this?
Yeah, it makes sense.
That's great. So now we are saying that we have this second machine, and we will see that whether this is valid or not. So, so this is so who will tell me that this is valid or not? Let me see. So Darian, do you think that this machine is valid? The second machine, this one, oh, this one, is this valid FA? Darian, are you there? Okay. Okay. So this is valid. You are saying this is valid. Okay. Yep, this is valid. Good. Uh, Now we will see that what regular expression this machine can give you. So now when you have this machine and I ask you write the regular expression, let's say, so because whenever your FA has start state and that state is also the final state, for sure it will accept lambda. So this will accept lambda, one thing for sure. Okay, look at this one. And then what this machine will accept after that. So now if you see this, you can have A, you can start with A, you can start with B, and then you have 1A, and then you have so if you notice here, you can start with A, you can start with B. That's not a problem. And once you reach here, you can have as many B's and then A and then as many A's. So it means initially you have A plus B whole star. Don't care, start with A, start with. But is it possible that you have B as a last letter and this machine will accept that word? Look at this one. When you have B, you are here. And this is not the final state, and here you have loop here as many b's, it will always be at the non-final state. To reach to the final state you need a, so or you are here, you have a, so it means we don't care whatever the size of the word, it start with a, it can start with b, but the last letter must be a. So a plus b whole star a. So this is the regular expression of this machine plus lambda. This whole thing is a regular expression of this machine. Okay, words that do not end in b and have lambda. So now we will see this another machine here. It has uh, first of all, it is valid or not, start state, and then A and B, A and B. So this is valid. Okay, it is take care of garbage collection and deterministic. So now you can start with B, you can start with A, so no problem. You can have as many B's and you can have as many A's, no problem. But to reach to the final state, you must have A with B, you will not able to reach that. And this machine does not accept lambda. Like this one, it accept lambda, it does not accept lambda. So it is just A plus B star A. So this part. Okay. So if so, this is a different machine from this one. It is good. And we have this machine. So now so let's see what is the regular expression of this machine. So so if you see here, you can have first of all we check that is this a valid machine or not. So B A good, B A good. So it is taking care of unique output and all outputs. This is valid. It's one start state, all letters. And now we will see that whether what is the regular expression of this machine. So you can so how we need to write the regular expression this way. So B star, it is B star A and then B star. So this is one path which will leads you to the final state. But might be you want to go after that, you think that you don't want to finish here, you want to choose again the next ride. Okay, if you want to take next ride, this is minimum, this is minimum you need for this machine. Okay, but what happen if you choose the next ride? Okay, let's do after that. And what is that? A and then B star, A and B star, and this is your choice. Might be you want to take this ride or you don't want to take this ride. How we give this? By putting lambda star here. This will gives you, if you don't want to take this ride, so then you will get lambda because of star. If you want to take this ride, it is good. So this is a regular expression of this language. Okay, so that's the idea behind that. And if you want to write the if you see here, it has always odd number of a's. So 1a, 2, 3 a's, 4, 5 a. So whatever the word it will accept, we don't care how many b's there, but it has always odd number of a's. So an odd number of a's. Okay, guys. So now let's see the next slide. So we have this uh, machine here, and we see that how we write the regular expression of this. So to reach to the final state, first of all, is this a so now who will tell me that this is valid or not? Gunnar, you think that this is valid FA? If this is valid, how it is valid?
Yes, it's valid. It has a start state and a transition for each letter in the alphabet.
Very nice. What else? Unique output from,
Finite
yes,
finite
deterministic.
transitions.
Yeah, deterministic. So three checks. Start must be one start state, exactly one start state. Every state should have one letter, and every state should handle A and B. Okay? So these are the three checks. So now we are saying how we write the regular expression of this machine. Now, if you see that here to reach the final state, what you need? A, and A. Okay. A, we need to reach to the final state. This is minimum what we need. You can start with B. You can have A and then come back here B, A, B, A, B. You have a loop here. So it is A plus B whole star. Once you reach to the final state, then you have a loop here, A plus B whole star. So this is basically your regular expression of this machine. Okay. So yep, that's it. So what I'm just explaining, so this is it's English, in nice English, its description. You can read this. Okay, so now we are saying that FA that is, okay, I want to create this by myself. So let me add a new slide here. Start, start. So let me add a new slide so then I can. So what we have here, so we want to create an FA that accepts all words that have different first and last letter. If so, it means if the first word, if the word begins with A, it should be ended with B, or so vice versa. Okay, so this is so means that the if you have a word, if it start with A, the last letter should be B. If it starts with B, the last letter should be A. So different first and last letter. We have a state. If it is start with A, it should end with B. If it starts with B, it should end with A. This is what we are saying. This is the minimum requirement for this FA. Start with A, end with B, start with B, end with A. So now if it start with A and end with B, you might have more than one B there. It does not harm us because still it is B. Yes. If you start with B, end with A, you might have more than one A there. It will not harm us because it is still A. If you start with A, you might have more A here, let's say, and then B. It is the same thing. Multiple start with A and it does not harm us. If you start with B, you might have more B's here and then A. So it is the same thing. So start with A, start with and with B, start with B and with A, same thing. But you this gives now flexibility that you have more than one A's or more than one B's in the start and end. But it respect the restriction. If starting is A, ending is always B, starting with B, ending is always A. Okay. What happen if you have a word something like this A and how I can say let's make a scenario. So if you have a word A here, and then okay, so let's say if you are here A and 2A, or A, B, and then A. Yes, A, B, and A. So you start with A. Look at this one. So you go here, A, B, you reach to the final state, and then A. This is wrong. It should not be accepted, yes? So because the last word is again A, we don't want this. We want it should be always B. So in this case, here we go back to here again if it is A. Okay? And the same is true here. We go back if it is B. So B, A, if it is B, this goes back. Always A will take you to the final, B will take back to the final from this one. So now I think that this is complete. If we check that first state A and B, second state A and B, third state A, here, second state B and A, final state B and A. So every state is handling A and B, and it maintain the check what we want to do. Like start with A and with B, start with B and with A. This is the regular expression of that. And if you see this exactly, this is what I draw here. But I mean, what you need to do, if you try to draw everything in one shot, it might be not easy job for you. So this technique which I just explained to you, first draw the minimum thing and then make it complete all scenarios, and this will be helpful. Okay, so think this way. This is a thinking process of this. Okay, so yeah, that's the regular expression of that. So this is just we have this word, and I'm showing here the how you go to this machine. uh, A, A, B, B, A, and again A, and then B and B. So this is basically we are showing that how we traverse here. So this traversing I shown here to you. Okay. So we are good with this. So now this is even language. So you have a word which will accept all number of A's and number of B's are even. So if you see this, it is very easy. Start state and the final state. Every state is taking care of A and B, A and B, A and B, A and B, A and B. So this is good. So this check is done. Start state is there, all letters. So this is valid FA. And if you see this, you always have uh, what do you call the even number of letters. Either you always have either two B's or two A's, or if you have A and B, so always in that you will have two A's and B's. Number of A's and number of B's will be even. So this is this machine, and I think that that's it. So we done this chapter. So this is our second week and we are going very well. We have to finish 19 chapters and we finish our fifth chapter today. So guys, any question in this? Otherwise, I move to the next chapter. So are you guys good with this? What I explained in this chapter? Anybody has any confusion, any question? No? Okay, so I want you to attempt the quiz now. And you have a quiz. So if you attempt the quiz right now, so you can do this in the class time. Are you ready to attempt the quiz? What is uh, so Quinton? What is crashing you? What is crashing? Can you give it is where an input is not handled by yes. And let's say if you have a word, if you have a word, uh, now look at this one. I give you one word A, B, B for this machine. What will happen with this word, Quinton? Is this accept or reject? Is this accept, fail or pass? Or fail or reject, crash? A, B, B for this machine. Why? Yeah, it goes to the final state, so it will accept. So this word will be accepted by this machine. Yes, it's a valid word because it reaches to the final state. Yes, very good. Now I give you this word A, sorry, B, A, A. What happened? It goes to the stop state. We don't say stop state. We call non-final state because top state. Yes, you're right. It goes B, A, and A. So does it finish the whole word or some letter left of this word? No letter left of this word, but the last letter we completely traverse, scan the whole word, we finish the whole word, we completely scan the whole word, and we end with non-final state. So it means that this word will be rejected, but this is fail. It will fail. This is fail. Okay. And if I give you this word, uh, B, or let's say A, C, and you see A, we have A, but we do not have C, and we have something left over, and we are not handling in our machine, and this is rejected, but this will crash. Where you have a word and you have a letter, you word completely, you do not scan the whole word, you are somewhere in between or at end, but you do not know how to where to go on this state is not handling that input, so this is called crash. Okay, so this is called crash. Okay, so thank you very much, no problem. Any other guys? So guys, please ask a question. So I mean, I always appreciate questions if you ask, so that makes me alive because the normal days you wake up 6 o'clock, take shower, go to the class, fresh. Here, man, I wake up at 9 o'clock from bed to the chair, so I'm also sleeping. So you ask me a question that makes me alive and makes me wake up. So please ask me a question. So this is good. Now, if you have no questions, so I think that I like to go to the next chapter then. I will not stop here because we have so much time. So, chapter 6. So let me first post this chapter so you will also have access of this chapter. How I do this? Modules. And I need to file, new file. This is chapter 6. Add item. Okay, so I add chapter 6 here now under May 18. Oh, sorry, this is May 19. So I add it here, chapter 6, and it is published, so you can have access of that. So I hope that you can see this chapter now in your canvas, and it is there now, chapter 6. Make sure that when we finish chapter 9, we will have a quiz. We will have the exam. Uh, Now let me open this chapter for you. Okay, so this is your transition graph. Actually, we are saying that if you have your so first of all, this is called transition graph, and the definition and the shortage, the small way we can write this as TG. Okay, so now we are saying that if you have a machine, so can anyone tell me that is this a valid FA or not? Anyone?
Yes, I think it is.
It is valid FA. Very good. So it has, if you see this, it is taking care of garbage collection, and so this machine will accept only one word, which is BAA. Okay. And if you have it, it will only take care of two things: fail and accept. Okay, in case of reject, uh, no crash there. So now we are saying that if that is the case, this machine will accept only one word. Why we are bothering too much? Why we are doing this? We know that this is not a complicated machine. It will only accept BAA, and let's say it's a controlled environment where you know that you will never give wrong input. Input is also controlled by some program. It will never happen that you will get wrong input. So then why we are wasting the resources and we are taking care of the garbage collection? So, but if you draw FA will always do that. Okay. So to ease this thing, we have a new way of defining the language. This is called a transition graph, TG. So TG is bit relax with FA. TG says you will have the same thing. So B, so if you see this, this will accept BAA. Okay. So TG says, look at this one. So if you are here, if you give input BA instead of letter, now you are passing a word as a label on the edge, and then A. So BA and A, this will lead you to the valid word. Or if you have, and that's it. Just look at this one. So B and A, B, all possible things you are handling here, and oh, there is no way to reach there. So now this is all garbage. Okay, and you don't need to do that. So it says that only this thing. So now what you did actually, you reduce, because when you have more number of states, it means more resources. When you have less number of states, it means less resources, less computation, less computational cost, more fast, more real time, and more good. And if you have more number of states, more computation, more resources, slow. It is slow. It will reduce the speed of the process. Okay. So now here you see that there's something which you are doing with 1, 2, 3, 4, 5 states. Now you are doing this with 4 states. Okay. And then it says that, man, if you are doing the same thing, BAA, why you bother so much? Why you are handling all these complex things like this? Can we make it more simple? We say just BAA, because if it allows you to add more than one letter word here, who stops you to put the third A here? Why we have this state? We just reduce this to the two. Look at this one. And all else, and AB is going here. Yes. If it is taking care of all else, and we know that input is controlled input. Why we are doing all these things? We do not even need to do that. This is perfect. That's it. You start final BAA. This is arrow here. Job is done. This is valid TG. This is called TG. You do not need to do the garbage collection. You do not need to worry about the letter by letter, which is the case in FA, and you do not need to do the all other things. So this is called your TG, and you can spend this thing here. Okay, and now if it says that the input. So in this case, now look at this one. So if I pass a word BAA to this machine, this will be accepted. If I pass a word B, you are here, you don't know what happened with just B, it will be rejected. But this is the second category of rejected. It is called crash. So it will crash. So TG does not take care of garbage collection. TG does not handle letter by letter input. You can pass word there. TG can crash also. Okay, so the input crashes, the machine crashes, input is rejected. Two ways of input to be rejected: when an input that has not been completely read, which I just explained you, reached a state that it cannot leave because there is no outgoing H that it may follow, the input or machine crashes. Exactly what I just explained you in the previous chapter and the here. So you have a machine, you have an input, you are reached that input, and you do not know how I go from this state with this input. You are not handling that, and you are stuck, and you machine will crash. It will be rejected, but it will be crash. It will not fail. Okay, so execution then terminate, and input must be rejected. That's the idea behind that. So any question about the TG? Uh, so I think that I don't want to actually go and continue this. Because this will be too much stuff for you guys. I want to stop here, and I want to finish this chapter in next class. And I think that we are good at this time till this. I just gave you idea. I uploaded this, so read this chapter, and I will finish this chapter in next class. It's not too long, and we can finish this. Oh yeah, it is long. So we can finish this in next class. Okay, guys. I think that we are done. Let me stop the recording.